Hi class, me Mr. Morris again. This is another video from our gas laws series. We're moving on to the next law. So this is technically video number 3 with some example problem videos scattered in between. Okay. This gas law is Gay-Lussac's law. That's the one we're going to look at today. Gay-Lussac's law relates pressure and temperature. So this is the way it works. We're talking about the relationship between pressure and temperature. If the temperature increases, the pressure inside the container increases. So we're talking about pressure pushing out. Okay, so if we heat something up, you think about popcorn, that's an example. Those popcorn kernels, they have a little water inside of it, and as you heat it up, it builds up pressure. So the reason for that is those water molecules turn into gas and they start bouncing around. They're hitting the sides of the container more frequently. That pressure builds and builds and builds and builds until it reaches a point where it explodes and you've got this popcorn turning inside out, and it's a totally different substance at that point. But we'll get into the examples. If the temperature increases, the pressure inside the container increases. If the temperature decreases, the pressure inside the container decreases. You do need to know that if we're talking about Gay-Lussac's law, we have a rigid container. And rigid just means the volume is not easily changed. Like a popcorn kernel. You can't really swell or expand the popcorn kernel without breaking it open. So that's why it changes. It bursts and turns into this fluffy white popcorn. Okay. So why is this? It's because if the temperature is increased, that means the gas molecules move faster. They collide with the walls more often. And if they collide more often with the walls, that means the pressure is building. Because the volume stays constant, the only thing that can change is the pressure. So we don't have the volume increasing. It just stays the same because it's rigid walls. Okay, so keep that in mind. Rigid walls, the volume stays constant. So if the temperature is decreased instead, that means the gas molecules move more slowly, and because they're moving more slowly, they hit the walls less often, and since they're hitting the walls less often, the pressure decreases. You've got to remember that the volume, and I've said it a couple times, this is just really important, the volume has to remain constant, so these containers have to have rigid walls. We got examples down here. It's a direct relationship between temperature and pressure. Don't forget your equation's important. P1 over T1 equals P2 over T2. Okay. If it's a direct relationship, that means that if one of the values goes up, the other one also goes up. If one value goes down, the other one also goes down. So pressure increases, temperature increases, pressure decreases, temperature decreases, and so on. Okay. All the temperatures have to be in kelvins, not Celsius. That's very important to recognize. Kelvin, not Celsius. The amount of gas, which is N, and the volume, which is V, are constant. Constant means they don't change. Okay, so we pretty well ignore them. That's why you don't find them in the equation. Examples, popping popcorn. We just talked about that a little bit. Those popcorn kernels, they can't handle the pressure because it gets so high, so they burst, and out comes this fluffy stuff. Okay, and then throwing an aerosol can into a fire may cause it to explode. Same thing, an aerosol can, if you were to throw that in the fire, the gas molecules move so quickly inside it that the pressure builds and builds and builds. And at any moment, if you had a pressure gauge, you could check and you could see that the pressure is getting very, very high inside the container. But the way that you really notice it is because there's suddenly an explosion. This is different than Charles' law because it actually pops or explodes instead of just swelling and getting bigger like if it was a balloon. Let's go on down to some example problems. That's kind of the qualitative side. We're going to do the quantitative side, or the part with some word problems with some numbers. It says a gas has a pressure of 0.370 atmospheres at 50.0 degrees Celsius. What is the pressure at standard, keyword here, standard temperature? Okay, standard temperature, don't forget that's 0 degrees Celsius, which is 273 Kelvin. Okay. Just don't forget that. So let's write down our variables. We've got 4 of them, P1, T1, P2, and T2. P1, T1, P2, T2. First pressure unit I see is atmospheres, 0.370, 0.370 ATM, atmospheres. All right, 50.0 degrees Celsius. Don't forget, anytime you look at your temperature, check to see if it's in Kelvin. If it's not, you got to turn it into Kelvin. We do that by adding 273.0. So if I do that, 50 plus 273, you get 323.0 Kelvin. Pressure 2, that's what I'm looking for. So I'm going to put a question mark here. And then T2 is standard temperature. Again, 0 Celsius is 273 Kelvin. So we're going to do 273.0 Kelvin. And let's do our problem. P1 over T1, so 0.370, that's P1, over 323.0, which is T1, equals P2 over T2. P2 is our unknown. I'm just going to call it P2. And then T2 is 273.0. Okay. Now I want to cross multiply again. That's just normally the easiest way to solve these problems. You may be good enough at algebra, you can work through some other methods, and that's fine. But just to be safe, that's what I'm going to do is cross multiply 323.0 times P2 and 0.370 times 273 on the. So when I do that, I'm going to get 323.0 times P2, 323.0 P2 equals, let's see, 0.370 times 273.0, I get 101.01. Let's just round it to 3 sig figs. 101. You could keep that 0.01. It probably won't really change the sig figs, and if it does, I wouldn't count wrong, as long as you round it correctly at the end. At the end, we need 3 sig figs. Okay, so now I want to get P2 by itself. To do that, I'm going to have to divide both sides by this 323. So P2 equals 101 over 323.0. Okay, I'm not really going to have room to write that down here, so I'm going to move it up here and put P2 equals, let's solve it, 101 divided by 323.0. I get 0.313. 0.313, and our units are atmospheres, because our units have to match the units of pressure that were given above. All right, that's it for this video. I'll probably do another one again, showing you the last 2 example problems, but otherwise, I'll catch you in the next video. This was Gay-Lussac's law. We have one more law we're going to talk about, and that is Avogadro's law. I'll catch you on that video.